Okay. So why are frames so important? Because of the power of frames, we can construct complex reference frame transformation with pretty much no programming effort required from you. But you have to load all the needed kernels, and the principal benefit of this frame capability actually doesn't come from frame transformation routines that simply give you matrices. It comes from high-level geometry routines that compute quantities based on frame transformations or compute vectors based on where frame transformations are done behind the scenes. And the remaining pages illustrate some typical uses of frames. So let's look at a very simple example. You have two instruments that are rigidly mounted on a spacecraft. In this case, it's Cassini ISS narrow angle camera and Cassini ISS wide angle camera. And you want to know angular separation between bore sides of these two cameras. Well, that's a very common thing. You want to know where, how much misaligned the images taken by these cameras are. So if you have frames kernel that defines fixed offset frames for these two cameras with respect to the spacecraft frame, all you can do to determine that, you need a call to px form that computes rotation from one frame to another frame, in this case from narrow angle camera frame to the wide angle camera frame, at any time really, because these are fixed transformation. Then, by retrieving bore side directions for each of these cameras and their corresponding frames, in this case, NAC bore side in the NAC frame and WAC bore side in the WAC frame, you can rotate one of these bore sides, in this case, NAC bore side, from the NAC camera frame to the WAC camera frame using this matrix, and then you simply compute angular separation between these two bore sides to determine this angle. To do these calls, of course, you need to load the frames kernel, which contains these frame definitions. You also need to load camera I kernels, which provide bore side definitions with respect to the corresponding frames. And you're likely to need leap seconds kernel because you have to do some time conversion to arrive at this ephemeris time. Well, something a bit more complicated and very common. You have a camera mounted on a spacecraft, and you want to make sure that this camera is not exposed to the sun. That's a very common constraint, that instruments cannot look directly at the sun or be within sun direction by a certain angle. Well, you can very easily do it for this narrow angle Cassini ISS camera with a single call to SPK pos. In this call, you will ask for position of the sun as seen from Cassini's spacecraft directly in the camera frame. So it will return you sun vector. Then you will compute angular separation between the sun vector and bore side of the camera using the same frame that you retrieve from the I kernel. And we'll compare this angle to certain constraint to see if you're in trouble or not. And if the angle is too small, well, you're in trouble. You're looking too close to the sun. You can burn your camera. It seems like it's just one call that does everything for you, but a lot of data is needed in SPICE world to make this call. You're looking for this vector. In order to compute this vector, SPICE needs to determine position of the sun and position of the sun with respect to Cassini. And for this, it needs to know the position of the sun with respect to solar system barycenter, position of the Saturn system barycenter with respect to solar system barycenter, position of Cassini with respect to Saturn, add all these vectors in an inertial frame, compute transformation from the inertial space J2000 frame in which these vectors were added to the camera frame, and then return this vector to you. All of this is done behind the scenes, and more importantly, not just this, but aberration corrections are included. So more iterations are done to make sure that this vector takes them into account. To do this, of course, you need to load quite a bit of data, leap seconds to do time conversion, mission frames kernel that defines spacecraft and camera frames. You need spacecraft's clock kernel because you're going to be reading information from these C kernels. Camera I kernel is where you will fetch the bore side information. It's not shown here on this slide. You also need planetary ephemeris SPK file, spacecraft SPK file in order to get all these wonderful position vectors. And you need to have spacecraft C kernel to provide orientation of the spacecraft. So even more complicated situation in this case, we want to find elevation of the sun as seen from the landing site. You can do it with a similar call to SPK pos. You ask for position of the sun as seen from the probe. in the probe local level frame. Local level frame in this case is defined with z-axis pointing down and x-axis pointing towards the pole. Then you can convert the vector returned by this pole to latitude and longitude, which are equivalent to azimuth and elevation, but you need to adjust the elevation sign to be positive, because the z-axis pointing down, it will be negative if the vector will be above horizon. And you may optionally adjust the azimuths to be within the 0 to 2 pi range if the value returned by this routine was negative. So one simple call answers your question, but again, a lot of data was needed to do it, including positions of these bodies with respect to each other, orientation of the body on which the lander landed, and orientation, fixed orientation of the stopocentric local level frame with respect to this body. So here's a more local situation. You have two sensors, two magnetometer sensors that were mounted on two solar panels of the MGS spacecraft. And in order to process data for these magnetometers, the team needed to know two things. It needed to know relative rotation between the two frames associated with these magnetometers such that the data could be rotated into a single frame for processing. And they also needed to know relative location of these magnetometers in a spacecraft frame in order to subtract the interference from the various magnetic fields generated by the spacecraft. For computing relative location, a single SPK EZR call in which position of one magnetometer sensor mounted on the -y panel, it had this name, was computed with respect to another magnetometer mounted on the other panel, directly in the spacecraft frame at whatever time was requested. And this call to PX4 computed rotation from the +y sensor frame to the -y sensor frame. Well, because this chain included multiple gimbals which were articulating, each of these solar arrays had 2 degrees of freedom, there needed to be C kernels providing these rotations, and this was provided in the solar array CK files. And of course, the magnetometer frames had some fixed offset with respect to the solar array frames, which were provided in emission frames kernel file. To compute locations, there was a location structure SPK, which provided fixed offset between various points within spacecraft bus to the first gimbal, to the second gimbal, and then to the magnetometer. Each has a fixed offset and is specified in a specific frame. So underneath, behind the scenes, SPICE was able to compute each of these vectors in the corresponding frame first, then rotate them all to the common frame, and then to do addition to compute this green vector. So again, it was just 2 calls if all the data is available. Fairly straightforward and simple. Well, that's something similar. You try to compute off-pointing angle for MGS high-gain antenna, which had 2 degrees of freedom articulating antenna. Off-pointing was the direction to the Earth, and in this case, we just asked for position of the Earth as seen from the spacecraft and the high-gain antenna, and SPICE took care of computing all the offsets and all the rotations between the various frames involved in these chains. And very similar situation for the landers, where we needed to know the position of the scoop, which was digging a trench on a Mars polar lander as seen in the camera, in one of the cameras mounted on a mast. This green vector can be done with a single SPK EZR call, where we request the position of the scoop, which would be a reference point at the top of the scoop, with respect to the surface frame. This is origin of the surface frame, or with respect to the camera, in this case, with respect to the surface frame. There are 2 calls here in a surface fixed coordinates, so that would give us this vector. And for the camera case, we will be asking for position of the scoop as seen from the position of this left eye of the camera in that camera's frame directly, so we can find it in the image. And again, we have 2 manipulators here for which rotations in each joint were stored in the CK files. In this case, it was a body angle CK file. And for the mask, the orientation of the camera, which had 2 degrees of freedom, was stored in a camera C kernel file. There was also a lander C kernel file that provided the tilt of the whole lander relative to the surface fixed frame. So all these rotations and transformations between different frames were combined together in these calls. And the vectors that were computed in a single frame were then rotated in the frame of interest. That's it. So I think the main message of this tutorial is that if a guy like Mark did a good job putting all the kernels together, there isn't much you need to do. You just need to get his meta kernel, load it, see what frame names are, what body names are, and boom, you're in business. Whether using his web geocal or using your own application, and just load these kernels and compute all kinds of things very, very easily.